Hello, my name's Tyler Fourthunders. This is my FEA project. So the diagram around this project was to simulate a lab pull-down machine, focusing on the cabling and pulleys in the system, showing that there's constant tension throughout the cables and showing the stress and strains from the cable onto the pulley itself. In order to create something like this, creating a cable apart, this radius of this curvature needs to match the radius of your pulley, so 2¼ inch. We're going to create our cable as 2D planar deformable wire. Looking at creating how I created the pulley, you can see that radius matches the radius of the curvature. So 2¼ inch. Also had a inch radius cutout for my inch bolt for the boundary conditions later on. So creating the pulley, 2D planar, deformable shell. So going on the properties, I assume that this is like aluminum pulley. So we need two properties for our material behavior. So Young modulus and Poisson's ratio. These are both in PSI, except Poisson's ratio. Because I'm using inches and pounds. So going on the cable. So I'm assuming it's like a steel core cable, just using the properties of steel in PSI. So going on, we'll look at the pulley first. So when making the pulley, just select solid homogeneous in our sections. Have your material select for your lumen you just created. Select this box because we're assuming it's a 1/2 inch pulley. Then creating the cable. We're going to do the same thing, except we need to make sure our type is beam. We need to select a profile. So we're going to assume it's a circular profile, and our diameter was 0.24 inch, so 0.12 inch radius. So last thing we need to do here, select beam orientation, select the whole thing. This shows just the direction vectors of our beam. So create your assembly. After that, we're just going to use a static general. Pretty much everything's default. We don't need to have this turned on. We're not going to see any large displacements in our part. Going on interactions. So this is important. We need to create a surface contact interaction between the pulley and cable. So we need to select our main surface as the outer diameter of our pulley. Secondary surface is the cabling itself, selecting all those elements. Second main point is to have node to surface as our method. This just allows each nodal point to be checked to see if it's phasing through our part. For our contact, we also need to have selected, we need to have a tangential behavior and a normal behavior. So we're going to assume it's frictionless. And in normal behavior, we're going to have hard contact and allow separation after contact. Last thing here is to make a coupling constraint. So making control point at the center of your pulley. And we're going to strain this inner diameter hole of our surface of the pulley to this control point. So select your control point as the reference point and that inner diameter surface as your surface point. Then constrain all degrees of freedom to that reference point. This is important because now you're able to apply boundary conditions to this reference point. So we're going to strain it in both horizontal and vertical direction, but allow it to rotate. Last boundary condition is we're going to strain this top left corner of our cable in the U1 direction. And then we'll also be applying a downward load of 100 pounds to our bottom right end of the cable. So going on to the mesh, we'll look at our pulley first. So when creating our mesh for our pulley, we need to select our element type. So we are going to use constant plane stress elements, triangular elements, so CPS3. So just make sure all these are selected. Going on to our cable. Since these are beam elements, we need to mesh them with beam elements. So make sure beam elements are selected. We're going to use the cubic formulation. So make sure it has B23 elements. Important thing here is to see the curvature properly. So I just put a bunch of elements in that curvature point. And now going on to the job, we'll run the job. So now our simulation should show constant stress throughout our part. So we can see, we do see the correct stress applied at the bottom right end. And as we move through the part, let's see if I can get the correct notes, we do see about the same. Top left end, same here. And we move through. It's about, yeah, it shows the correct stress. Another way to show axial tension is go to the section force. It should show an axial load of 100 pounds. So we look at the top left end, it does show 100 pounds being applied axially. And as we move through the cable, roughly about 100 pounds throughout the cable, bottom right end. Last check to show this is working properly. We look at a reaction force. So at the center of pulley should show a reaction force countering a 100-pound downward load. And it also horizontally shows that axial force of 100 pounds as well here at a boundary condition. Reaction force vertically. So second method, when you want to add more pulleys to your system, you need to switch over to using truss elements. So this is how I design my cabling system using two pulleys here. So you're going to use the same properties. So here, when you're creating your section for your new cabling, make sure you select the type as truss elements. Now you're going to have to calculate and add your cross-sectional area directly using the diameter of your part and using the same properties. There's no need in that beam orientation no more. Your step is going to be the same. Now in your interaction, so you're still going to use the same frictionless normal behavior contact. What now you're going to add is a constraint on your cable to the reference point. So using a coupling constraint, select your control point as your reference point and this curved surface as your surface point. Constrain all the degrees of freedom to that point for both pulleys. Then going on to load, select the same boundary conditions at both reference point and lower left end. We're using the same downward load here. So mesh your cable the same way. So we're using truss elements this time. So select truss down here and make sure it's on T2, D2 elements. And then do the same thing with seed, just seed your corners very heavily. Now I'll show what your job looks like. So the reason you can't use beam elements when using more than one pulley is because the beam bending doesn't show the axial load constant throughout the elements. So truss elements do a lot better at carrying that axial load. So we can see that here. We go to S11, we see bottom left end shows the axial load as being constant at the part. Only problem here is it doesn't show the axial load carried throughout the bends itself, but it does show here. And now looking at our reaction forces, we see correct reaction forces at our pulleys. And then lastly, correct reaction forces at our boundary condition here at the bottom left end. Thank you.